Our universe is vast, achingly beautiful, remarkably simple in some ways, intricately complex in others. From our universe's great richness, we'll need only a few basic facts that I'll now lay bare. The Big Bang. Our universe was born in a gigantic explosion 13.7 billion years ago. The explosion was given the irreverent name, the Big Bang, by my friend Fred Hoyle, a cosmologist who at that time, the 1940s, thought it an outrageous, fictional idea. Fred was proved wrong. We've since seen radiation from the explosion, even in just the last week, as I write this, tentative evidence for radiation emitted in the first trillionth of a trillionth of a trillionth of a second after the explosion began. We don't know what triggered the Big Bang, nor what, if anything, existed before it. But somehow, the universe emerged as a vast sea of ultra-hot gas, expanding fast in all directions like the fireball ignited by a nuclear bomb blast, or by the explosion of a gas pipeline. Except that the Big Bang was not destructive, so far as we know. Instead, it created everything in our universe, or rather, the seeds for everything. Galaxies. As our universe expanded, its hot gas cooled. In some regions, the gas's density was a bit higher than in others, randomly. When the gas got cold enough, gravity pulled each high-density region inward on itself, giving birth to a galaxy, a huge cluster of stars and their planets and diffuse gas between the stars. The earliest galaxy was born when the universe was a few 100 million years old. There are roughly 1 trillion galaxies in the visible universe. The largest galaxies contain a few trillion stars and are about 1 million light-years across. The smallest, about 10 million stars and 1,000 light-years across. At the center of most every large galaxy there is a huge black hole, one that weighs 1 million times the sun's weight or more. The Earth resides in a galaxy called the Milky Way. Most of the Milky Way stars are in the bright band of light that stretches across Earth's sky on a clear, dark night, and almost all the pinpricks of light that we see in the sky at night, not just those in the bright band, also lie in the Milky Way. The nearest large galaxy to our own is called Andromeda. It is 2.5 million light-years from Earth. It contains about 1 trillion stars and is about 100,000 light-years across. The Milky Way is a sort of twin to Andromeda, about the same in size, shape, and number of stars. Andromeda contains a gigantic black hole, 100 million times heavier than the Sun, and as big across as the Earth's orbit. The same weight and size as Interstellar's Gargantua. Solar System. Stars are large, hot balls of gas, usually kept hot by burning nuclear fuel in their cores. The Sun is a fairly typical star. It is 1.4 million kilometers across, about 100 times larger than the Earth. Its surface has flares and hot spots and cooler spots, and is fascinating to explore through a telescope. 8 planets, including the Earth, travel around the Sun in elliptical orbits, along with many dwarf planets, of which Pluto is the most famous, and many comets, and smaller rocky bodies, called asteroids and meteoroids. Earth is the 3rd planet from the Sun. Saturn, with its gorgeous rings, is the 6th planet out and plays a role in Interstellar. The solar system is 1,000 times bigger than the Sun itself. Light needs 11 hours to travel across it. The distance to the nearest star, other than the Sun, Proxima Centauri, is 4.24 light-years, 2,500 times farther than the distance across the solar system. In Chapter 13, I discussed the awful implications for interstellar travel. Stellar death, white dwarfs, neutron stars, and black holes. With the shell's fuel spent and the Earth fried, the sun will shrink to become a white dwarf star about the size of the Earth, but with density 1,000,000 times higher. The white dwarf will gradually cool over tens of billions of years to become a dense, dark cinder. Stars much heavier than the sun burn their fuel much more quickly and then collapse to form a neutron star or a black hole. The sun and Earth are about 4.5 billion years old, about a third the age of the universe. After another 6.5 billion years or so, the sun will exhaust the nuclear fuel in its core, the fuel that keeps it hot. The sun then will shift to burning fuel in a shell around its core, and its surface will expand to engulf and fry the Earth. Neutron stars have masses about 1 to 3 times that of the sun, circumferences of 75 to 100 kilometers, about the size of Chicago, and densities the same as the nucleus of an atom, 100 trillion times more dense than rock and the Earth. Indeed, neutron stars are made of almost pure nuclear matter, atomic nuclei packed side by side. Black holes, more about them in Chapter 5, by contrast, are made fully and solely from warped space and warped time. I'll explain this weird claim in Chapter 4. They contain no matter whatsoever, but that they have surfaces called event horizons, or just horizons, through which nothing can escape, not even light. That's why they are black. A black hole's circumference is proportional to its mass. The heavier it is, the bigger it is. A black hole with about the same mass as a typical neutron star or white dwarf, say 1.2 times as heavy as the sun, has a circumference of about 22 kilometers, a fourth that of the neutron star, and 1,000th that of the white dwarf. Since stars are generally no heavier than about 100 suns, the black holes to which they give birth are also no heavier than 100 suns. The giant black holes in the cores of galaxies, 1,000,000 to 20 billion times heavier than the sun, therefore cannot have been born in the death of a star. They must have formed in some other way, perhaps by the agglomeration of many smaller black holes, perhaps by the collapse of massive clouds of gas. Magnetic, electric, and gravitational fields. Because magnetic force lines play a big role in our universe and are important for Interstellar, let's discuss them too before diving into interstellar science. As a student in science class, you may have met magnetic force lines in a beautiful little experiment. Do you remember taking a sheet of paper, placing a bar magnet under it, and sprinkling iron filings, elongated flakes of iron, on top of the paper? When you try to push two magnets together with their north poles facing each other, their force lines repel each other. You see nothing between the magnets, but you feel the magnetic field's repulsive force. This can be used for magnetic levitation, suspending a magnetized object, even a railroad train, in midair. The Earth also has two magnetic poles, north and south. Magnetic force lines depart from the south magnetic pole, swing around the Earth, and descend into the north magnetic pole. These force lines grab a compass needle, just as they grab iron filings, and drive the needle to point as nearly along the force lines as possible. That's how a compass works. The Earth's magnetic force lines are made visible by the aurora borealis, the northern lights. Protons flying outward from the sun are caught by the force lines and travel along them into the Earth's atmosphere. There, the protons collide with oxygen and nitrogen molecules, making the oxygen and nitrogen fluoresce. That fluorescent light is the aurora. Neutron stars have very strong magnetic fields, whose force lines are donut-shaped, like the Earth's. Fast-moving particles trapped in a neutron star's magnetic field light up the force lines producing the blue rings. Some of the particles are liberated and stream out the field's poles, producing the two violet jets in the figure. These jets consist of all types of radiation: gamma rays, X-rays, ultraviolet, visual, infrared, and radio waves. As the star spins, its luminous jets sweep around the sky above the neutron star like a searchlight. Every time a jet sweeps over the Earth, astronomers see a pulse of radiation. So, astronomers have named these objects pulsars. The universe contains other kinds of fields, collections of force lines, in addition to magnetic fields. One example is electric fields, collections of electric force lines that, for example, drive electric current to flow through wires. Another example is gravitational fields, collections of gravitational force lines that, for example, pull us to the Earth's surface. The Earth's gravitational force lines point radially into the Earth, and they pull objects toward the Earth along themselves. The strength of the gravitational pull is proportional to the density of the force lines, the number of lines passing through a fixed area. As they reach inward, the force lines pass through spheres of ever-decreasing area, so the line's density must go up inversely with the sphere's area, which means the Earth's gravity grows as you travel toward it. Since each sphere's area is proportional to the square of its distance ER from the Earth's center, the strength of the Earth's gravitational pull grows as 1 or R2. This is Newton's inverse square law for gravity, an example of the fundamental laws of physics that are Professor Brand's passion in Interstellar and our next foundation for interstellar science. The laws that control the universe, mapping the world and deciphering the laws of physics. Physicists have struggled from the 17th century onward to discover the physical laws that shape and control our universe. This has been like European explorers struggling to discover the Earth's geography. By 1506, Eurasia was coming into focus, and there were glimmers of South America. By 1570, the Americas were coming into focus, but there was no sign of Australia. By 1744, Australia was coming into focus, but Antarctica was terra incognita. Similarly, by 1690, the Newtonian laws of physics had come into focus, with concepts such as force, mass, and acceleration, and equations that link them, such as F Asra Ma. The Newtonian laws accurately describe the motion of the moon around the Earth and the Earth around the sun, the flight of an airplane, the construction of a bridge, and collisions of a child's marbles. In Chapter 2, we briefly met an example of a Newtonian law, the inverse square law for gravity. By 1915, Einstein and others had found strong evidence that the Newtonian laws fail in the realm of the very fast, objects that move at nearly the speed of light, the realm of the very large, and the realm of intense gravity, black holes. To remedy these failures, Einstein gave us his revolutionary, relativistic laws of physics. Using the concepts of warped time and warped space, the relativistic laws predicted and explained the expansion of the universe, black holes, neutron stars, and wormholes. By 1924, it was crystal clear that the Newtonian laws also fail in the realm of the very small. To deal with this, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and others gave us the quantum laws of physics, using the concepts that everything fluctuates randomly at least a little bit, and that these fluctuations can produce new particles and radiation, where before there were none. The quantum laws have brought us lasers, nuclear energy, and a deep understanding of chemistry. By 1957, it became evident that the relativistic laws and the quantum laws are fundamentally incompatible. They predict different things, incompatible things, in realms where gravity is intense and quantum fluctuations are strong. These realms include the Big Bang birth of our universe, the cores of black holes like Gargantua, and backward time travel. In these realms, a fiery marriage of the incompatible relativistic and quantum laws gives rise to new laws of quantum gravity. Truth, educated guesses, and speculations. The science of Interstellar lies in all four domains: Newtonian, relativistic, quantum, and quantum gravity. Correspondingly, some of the science is known to be true, some is an educated guess, and some is speculation. To be true, the science must be based on well-established physical laws, Newtonian, relativistic, or quantum, and it must have enough basis in observation that we are confident of how to apply the well-established laws. In precisely this sense, neutron stars and their magnetic fields, as described in Chapter 2, are true. Why? First, neutron stars are firmly predicted to exist by the quantum and relativistic laws. Second, astronomers have studied in enormous detail the pulsar radiation from neutron stars, pulses of light, X-rays, and radio waves described in Chapter 2. These pulsar observations are beautifully and accurately explained by the quantum and relativistic laws if the pulsar is a spinning neutron star, and no other explanation has ever been found. Third, neutron stars are firmly predicted to form in astronomical explosions called supernovae, and pulsars are seen at the centers of big, expanding gas clouds, the remnants of old supernovae. Thus, we astrophysicists have no doubt. Neutron stars really do exist, and they really do produce the observed pulsar radiation. Another example of a truth is the black hole Gargantua and the bending of light rays by which it distorts images of stars. Physicists call this distortion gravitational lensing, because it is similar to the distortion of a picture by a curved lens or mirror, as in an amusement park's funhouse, for example. Einstein's relativistic laws predict, unequivocally, all the properties of black holes from their surfaces outward, including their gravitational lensing. Astronomers have firm observational evidence that black holes exist in our universe, including gigantic black holes like Gargantua. Astronomers have seen gravitational lensing by other objects, though not yet by black holes, and the observed lensing is in precise accord with the predictions of Einstein's relativistic laws. This is enough for me. Gargantua's gravitational lensing, as simulated by Paul Franklin's double negative team, using relativity equations I gave to them, is true. This is what it really would look like. By contrast, the blight that endangers human life on Earth in Interstellar is an educated guess in one sense, and a speculation in another. Let me explain. Throughout recorded history, the crops that humans grow have been plagued by occasional blights, rapidly spreading diseases caused by microbes. The biology that underlies these blights is based on chemistry, which in turn is based on the quantum laws. Scientists do not yet know how to deduce from the quantum laws all of the relevant chemistry, and they do not yet know how to deduce from chemistry all of the relevant biology. Nevertheless, from observations and experiments, biologists have learned much about blights. The blights encountered by humans thus far have not jumped from infecting one type of plant to another with such speed as to endanger human life. But nothing we know guarantees this can't happen. That such a blight is possible is an educated guess. That it might someday occur is a speculation that most biologists regard as very unlikely. The gravitational anomalies that occur in Interstellar, for example, the coin Cooper tosses that suddenly plunges to the floor, are speculations. So is harnessing the anomalies to lift colonies off Earth. Although experimental physicists, when measuring gravity, have searched hard for anomalies, behaviors that cannot be explained by the Newtonian or relativistic laws, no convincing gravitational anomalies have ever been seen on Earth. However, it seems likely from the quest to understand quantum gravity that our universe is a membrane, physicists call it a brain, residing in a higher dimensional hyperspace, to which physicists give the name bulk. When physicists carry Einstein's relativistic laws into this bulk, as Professor Brand does on the blackboard in his office, they discover the possibility of gravitational anomalies. Anomalies triggered by physical fields that reside in the bulk. We are far from sure that the bulk really exists, and it is only an educated guess that, if the bulk does exist, Einstein's laws reign there. And we have no idea whether the bulk, if it exists, contains fields that can generate gravitational anomalies, and if so, whether those anomalies can be harnessed. The anomalies and their harnessing are a rather extreme speculation, but they are a speculation based on science that I, and some of my physicist friends, are happy to entertain. So they fall within the guidelines I advocated for Interstellar. Speculations will spring from real science, from ideas that at least some respectable scientists regard as possible. Of course, the status of an idea, truth, educated guess, or speculation can change, and you'll meet such changes occasionally in the movie and in this book. For Cooper, the bulk is an educated guess that becomes a truth when he goes there in the Tesseract, and the laws of quantum gravity are a speculation until TARS extracts them from inside a black hole. So for Cooper and Murph, they become truth. Of course, the status of an idea, truth, educated guess, or speculation can change, and you'll meet such changes occasionally in the movie and in this book. For Cooper, the bulk is an educated guess that becomes a truth when he goes there in the Tesseract, and the laws of quantum gravity are a speculation until TARS extracts them from inside a black hole. So for Cooper and Murph, they become truth. For 19th century physicists, Newton's inverse square law for gravity was an absolute truth. But around 1890 it was revolutionarily upended by a tiny observed anomaly in the orbit of Mercury around the Sun. Newton's law is very nearly correct in our solar system, but not quite. This anomaly helped pave the way for Einstein's 20th century relativistic laws, which, in the realm of strong gravity, began as speculation, became an educated guess when observational data started rolling in, and by 1980, with ever-improving observations, evolved into truth. Revolutions that upend established scientific truth are exceedingly rare, but when they happen, they can have profound effects on science and technology. Can you identify in your own life speculations that became educated guesses and then truth? Have you ever seen your established truths upended with a resulting revolution in your life? In these realms, for example, the energy of light has huge quantum fluctuations. They are so huge that they warp space and time enormously and randomly. The fluctuating warpage is beyond the scope of Einstein's relativistic laws, and the warpage's influence on the light is beyond the scope of the light's quantum laws. The phrase fiery marriage was coined by my mentor, John Wheeler, who was superb at naming things. John also coined the words black hole and wormhole, and the phrase a black hole has no air. He once described to me lying in a warm bath for hours on end, letting his mind soar in a search for just the right word or phrase. Warped time and space and tidal gravity, Einstein's law of time warps. The greater the slowing of time, the stronger gravity's pull. On Earth, where time is slowed by only a few microseconds per day, gravity's pull is modest. On the surface of a neutron star, where time is slowed by a few hours per day, gravity's pull is enormous. At the surface of a black hole, time is slowed to a halt, whence gravity's pull is so humongous that nothing can escape, not even light. Einstein struggled to understand gravity on and off from 1907 onward. Finally, in 1912, he had a brilliant inspiration. Time, he realized, must be warped by the masses of heavy bodies such as the Earth or a black hole, and that warping is responsible for gravity. He embodied this insight in what I like to call Einstein's law of time warps, a precise mathematical formula that I describe qualitatively this way. Everything likes to live where it will age the most slowly, and gravity pulls it there. This slowing of time near a black hole plays a major role in Interstellar. Cooper despairs of ever seeing his daughter Murph again, when his travel near Gargantua causes him to age only a few hours, while Murph on Earth is aging 8 decades. Human technology was too puny to test Einstein's law until nearly half a century after he formulated it. The first good test came in 1959, when Bob Pound and Glenn Repka used a new technique called the Mössbauer effect to compare the rate of flow of time in the basement of a 73-foot tower at Harvard University with the time in the tower's penthouse. Their experiment was exquisitely accurate, good enough to detect differences of 0.016 seconds, 1.6 trillionths of a second, in one day. Remarkably, they found a difference 130 times larger than this accuracy, and in excellent agreement with Einstein's law. Time flows more slowly in the basement than in the penthouse by 210 trillionths of a second each day. The accuracy improved in 1976 when Robert Vesser of Harvard flew an atomic clock on a NASA rocket to a 10,000-kilometer height and used radio signals to compare its ticking rate with clocks on the ground. Vesser found that time on the ground flows more slowly than at a height of 10,000 kilometers by about 30 microseconds, 3 seconds in one day, and his measurement agreed with Einstein's law of time warps to within his experimental accuracy. That accuracy, the uncertainty in Vesot's measurement, was 7 parts in 100,000, 0.007 of 30 microseconds in a day. The Global Positioning System, GPS, by which our smartphones can tell us where we are to 10 meters accuracy, relies on radio signals from a set of 27 satellites at a height of 20,000 kilometers. Typically, only 4 to 12 satellites can be seen at once from any location on Earth. Each radio signal from a viewable satellite tells the smartphone where the satellite is located and the time the signal was transmitted. The smartphone measures the signal's arrival time and compares it with its transmission time to learn how far the signal traveled, the distance between satellite and phone. knowing the locations and distances to several satellites, the smartphone can triangulate to learn its own location. This scheme would fail if the signal transmission times were the true times measured on the satellite. Time at a 20,000-kilometer height flows more rapidly than on Earth by 40 microseconds each day, and the satellites must correct for this. They measure time with their own clocks, then slow that time down to the rate of time flow on Earth before transmitting it to our phones. Einstein was a genius, perhaps the greatest scientist ever. This is one of many examples where his insights about the laws of physics could not be tested in his own day. It required a half-century for technology to improve enough for a test with high precision, and another half-century until the phenomena he described became part of everyday life. Among other examples are the laser, nuclear energy, and quantum cryptography, the warping of space, the bulk, and our brain. In 1912, Einstein realized that if time can be warped by massive bodies, then space must also be warped. But despite the most intense mental struggle of his life, the full details of space warps long eluded him. From 1912 to late 1915, he struggled. Finally, in November 1915, in a great eureka moment, he formulated his field equation of general relativity, which encapsulated all his relativistic laws, including space warps. Again, human technology was too puny for high-precision tests. This time, the needed improvements took 60 years, culminating in several key experiments. The one I liked best was led by Robert Riesenberg and Erwin Shapiro of Harvard. In 1976 to 77, they transmitted radio signals to two spacecraft in orbit around Mars. The spacecraft, called Viking 1 and Viking 2, amplified the signals and sent them back to Earth, where their round-trip travel time was measured. As the Earth and Mars moved around the Sun in their orbits, the radio signals traversed paths that were changing. At first, the paths were far from the Sun. Then they passed near the Sun, and then far again. If space were flat, the round-trip travel time would have changed gradually and steadily. It did not. When the radio waves passed near the Sun, their travel time was longer than expected, longer by hundreds of microseconds. Now, one of Einstein's relativistic laws says that radio waves and light travel at an absolutely constant, unchanging speed. Therefore, the distance from Earth to the spacecraft had to be longer than expected when passing near the Sun, longer by hundreds of microseconds, times the speed of light, about 50 kilometers. The shape that the team measured for the Sun's equatorial plane with the magnitude of the warping exaggerated. The measured shape was precisely what Einstein's relativistic laws predict, precise to within the experimental error, which was 0.001 of the actual warping, that is, a part in 1,000. Around a neutron star, the space warp is far greater. Around a black hole, it is enormously greater. Now, the Sun's equatorial plane divides space into two identical halves, that above the plane and that below. Nonetheless, shows the equatorial plane as warped like the surface of a bowl. It bends downward inside and near the Sun, so that diameters of circles around the Sun, when multiplied by p, are larger than circumferences. Larger, in the case of the Sun, by roughly 100 kilometers. That's not much, but it was easily measured by the spacecraft, with a precision of a part in 1,000. How can space bend down? Inside, what does it bend? It bends inside a higher dimensional hyperspace called the bulk. That is not part of our universe. Let's make that more precise. The sun's equatorial plane is a two-dimensional surface that bends downward in a three-dimensional bulk. This motivates the way we physicists think about our full universe. Our universe has three space dimensions: east-west, north-south, up-down. And we think of it as a three-dimensional membrane, or brain for short, that is warped in a higher dimensional bulk. How many dimensions does the bulk have? For the purposes of Interstellar, the bulk has just one extra space dimension, 4 space dimensions in all. Now, it's very hard for humans to visualize our three-dimensional universe, our full brain, living and bending in a 4-dimensional bulk. So, throughout this book I draw pictures of our brain and bulk, with one dimension removed. In Interstellar, the characters often refer to 5 dimensions. 3 are the space dimensions of our own universe, or brain, east-west, north-south, up-down. The 4th is time, and the 5th is the bulk's extra space dimension. Does the bulk really exist? Is there truly a 5th dimension, and maybe even more, that humans have never experienced? Very likely yes. The warping of space, warping of our brain, plays a huge role in Interstellar. For example, it's crucial to the very existence of the wormhole, connecting our solar system to the far reaches of the universe, where Gargantua lives, and it distorts the sky around the wormhole and around the black hole Gargantua. It is a fanciful drawing by my artist friend, Leah Halloran, depicting a hypothetical region of our universe that contains large numbers of wormholes and black holes, extending outward from our brain into and through the bulk. The black holes terminate in sharp points called singularities. The wormholes connect one region of our brain to another. As usual, I suppress one of our brain's 3 dimensions, so the brain looks like a 2-dimensional surface. Let me know in the comments if you want the rest of the theories explained.